This is 8.4 part 2, trigonometric substitution. Um, Recall when we do substitutions in this scenario, we would let x be in terms of a new variable, and it'll be the trig function this time. We're going to have three choices: sine, tangent, and secant, depends on the form. Notice that we have difference of square and sums of square. That's a difference of square as well in different order. Okay, so we have three possibilities. Now we did 1 and 2. You see this is the sums of square. That's a difference of square. Here is also a difference of square in different order. Number 3, you see that's 9 minus x squared. Okay, so which is that form, 9 minus x squared, or 3 squared minus x squared. So to do that, you have to do the substitutions, x be 3 sine theta. So now we're looking at number 3. The integral here, x squared over 9 minus x squared in square root. We will let x be 3 sine theta. Okay, so again, here's a substitution on the sides. Let x be sine of theta. Then the derivative of x is cosine of theta d theta. Every time we do the substitution, be sure to take the derivative of that variable immediately. You need it anyway, right? So be that. And because we need the cosine theta d theta, this time we'll replace the dx with cosine theta d theta. And I think we're ready to plug in, right? So I think we're ready to plug in, and just be careful here. Here equal integral, the top, what do you have, right? X squared, so that is sine squared on the top. And what do we have in the bottoms? It's 9 minus x squared in the bottom, square there, right? So I'm just writing the placeholder. In the x here is sine of theta. Actually, my bad. We let x be sine. The problem you see is, I didn't follow it carefully. You see, if you have 9, the size there, you have 9 minus sine squared, and we don't have the identities to use. And that is why we need to modify with an a, in this case 3. We need the 3 there, so that when you simplify here, you do have a identity to apply there, right? So be 3 sine theta is there. Okay, so I need an extra 3 there as I do the substitutions here. Okay, now again, don't forget that the dx also changed to 3 cosine theta d theta as well. Right, now let's simplify from here. If you simplify, let's see, equal, that's 9 sine squared in the top, right? So that become 9 sine squared of theta over, this is 9 minus 9 sine squared, don't forget, that is 9 minus 9 sine squared, and then take out 9, it's 9 times 1 minus sine squared on the bottom. Okay, so we get 1 minus sine squared there, and then you time 3 cosine of theta d theta. All right. Now, why do we do that? And again, you see the goal is the inside the denominator of the square root in the denominators. You see the identities here, 1 minus sine squared is cosine squared. Now the numerator is still 9 sine squared theta, but the numerators, it's become his square root of 9, that is 3. Now the 1 minus sine squared by the trig identity, what is this? This is cosine squared. But square root of cosine squared become cosine. You see that? This is why we do the substitutions by choosing 3 sine theta. So we have identities there to apply, and we could simplify it. Simplify the radical. You see the radical gone because we have perfect squares in the radical. Now from here we have the trig integral. That will be back to the previous section. How do we deal with trig integral? Well, we have only 2 ways to do. It's either we use trig identities or we use these substitutions. But before we do that, notice we have some cancellation going on there, right? So we end up with 9 sine squared. That is the function that is left over. You see this integral? Now it's just 9 sine squared theta d theta, right? And cancel out the denominator. All right, so how are we gonna simplify this? Well, if we only have sine, right? We don't have cosine. That means we cannot use substitutions. And if we cannot use substitution, we use trig identity. So what trig identities we are using? You see this one that I told you to remember. Again, that one is super important. The sine square is half of 1 minus cosine 2 theta, the so-called power reducing identities. Okay. Now that is useful is because when you simplify using the power reduction identities, you basically get rid of the power here, right? It's a 9. And using the identity that is half times 1 minus cosine of 2 theta d theta. Okay, then from here, from here I can integrate. That's not the problem, right? So we can simplify it here because whereas the 9/2 is a constant, we can take that out. And now you have write it with the different color. Here is where I integrate, so I change color. Antiderivative 1, well, it's theta. Okay, the variable is theta. The antiderivative cosine is sine 2 theta. But do not forget the chain rule. Or again, when you take a derivative, you time 2 because of the derivative of 2 theta. When we do antiderivative, we divide or time half. So that's what we have. And plus c. Now it seems to be done there, right? But then we're gonna have to switch back to the original variables. Okay, so now there's a bit of problem, unlike other one and 2 we've done. Here is the angles 2 theta rather than theta. Notice that the relationship between the x and theta we have here, right? So if you go back up here and look, if x is 3 sine theta, right? So then I know x over 3 is equivalent to sine of theta, right? And then from here, of course, I can draw the construct the right triangle. It's the same way we did before. By think of sine of theta is opposite over, right? So sine is opposite over hypotenuse, right? So we use that information. We can construct the right triangle with that information. Here's your theta, right? Opposite, where's opposite side? Opposite side is x, which is here, so that's an x. The hypotenuse is here, is 3. So you have x squared plus that size of the adjacent side squared for 3. Then when you solve, this remaining side would have a radical in it. So right, so square root of 9 minus x squared. If you've done a lot of the problem, you realize that the third side or remaining side in the right triangle will always be the quantity square root that we start at the beginning. If you see it, beginning. It's the beginning. See, that is the one. Like why? If you look at number 1 here, you see this remaining side we solve, the hypotenuse. This is that one. It's a root of 4 plus x squared, always. Okay. Now, in this right triangles, I can write sine and cosine theta and tangent theta in terms of x, right? Not the problem. But the problem is you have sine of 2 theta, which we don't have in this right angle triangle. So in order to simplify or rewrite this, you have to go back and use the, what did I say? Identity. You see that identities we use here? The so-called the double angle identity. Sine 2 theta is 2 sine theta cosine theta. So from here, you have to convert it back to the single theta there. So that's 9/2, and then you have theta minus 1/2 times 2 sine theta times cosine theta plus c. Okay, so that is the identity we use here. Sine theta is 2 sine theta cosine theta. All right. Now from here, I can substitute in from here, but at the same time, I think we can have this 2.5 cancel out. And final step here is rewrite that as 9/2. What is theta? Right, so sine of theta is x over 3. So theta is the sine inverse of x over 3, or the arc side of x over 3. So either way, so it's arc sine of x over 3. That is from the theta minus, what's the sine again? Sine is x over 3. So that is x over 3 times the cosine of theta. What's cosine of theta? Well, cosine is the adjacent side of hypotenuse. The adjacent is the square root of 9 minus x squared over the hypotenuse is 3. Okay? Plus constant. So that finished the example 3 here. Right? So that is the solution. Now let's look at example 4. The integral from 0 to 1 x cubed times square root of x squared plus 1. Notice this is a definite integral, right? So your answer is not just a function. It will be a numerical values represent the area. But anyway, we still have to go through all these procedures to find the antiderivative first before we use the fundamental theorem of calculus to plug in upper and lower limits to fit the problem. So that means it's going to be a bit longer. You got to go through everything here, and then you use the theorem at the end to finish, right? So number 4 again, right? You put it out here, right? 0 to 1. So you look at this, the one you have square root of x squared plus 1. Okay, x squared plus 1. And so what's the form? This is sums of square. Right, for the sums of square, this will be that one, right? X squared plus 1, or 1 plus x squared. So a is 1. So this one actually is a bit easy. With a is 1, so we're gonna let a or let x be tangents. Okay, so we're gonna let x be tangents of theta. Okay, tangents theta. Then your dx will be secant squared. Okay, so I always do that immediately before I forgot the dx. Now let's substitute in. Well, to make things easy, I will probably left off the upper low limits for now. So what it means is I only consider this integral for the moment, but keep in mind we're going to need to come back after we've done the antiderivative. So I only consider the indefinite integral there, right, without low limits. So let's do this first. Then it's after I use the substitutions here, let x be tangent, right? So that will turn into tangent cube there, and then you have the x squared plus 1 there, and then the dx, don't forget the dx will be the secant squared. So we have tangents here, tangents of theta, and we have a tangent squares here, right? And we also have the secant times the secant square d theta there. Okay, secant square d theta. Now, after you plug in and simplify, let's see what we get. You see here that tangent cube. That's tangent cube. This is what? This is tangent square plus 1 is secant square. So you have secant square, right, inside the square root, and that is secant square. I don't want to make it too long, so let's simplify this. Square root of secant square is secant, right? And then you multiply secant square, what do you get? Secant cube. So we end up with tangent cube times secant cube. Right, let's skip a little step there. And that becomes secant theta times secant squared becomes secant cube. And from here, he said, all right, so what do we do from this step? Well, that's the trig integral. And when you trig integral, you have to do what? Either substitutions or you use the trig identity. Since I have both tangent and secant, so I think it's perfect. It makes perfect sense to use substitutions. Let u be tangent or let u be secant. Now in this case, I don't think the tangent work You can try and figure that out, but apparently it doesn't work if you let UV tangents in the secant square and 1 secant left. Yeah, so we're gonna do another substitutions here. Right, so this time is the normal substitution we call the U sub because we often let U be, right? So in this case, I'll let U be secant theta. And that way, the derivative of U is secant theta times tangent theta, d theta. Okay, now why it works? Well, because I have what secant tangents here. So before we get there, we're gonna do a quick rearranging. Okay, so we have tangent there, secant there, so we save one of them. So that is, we should have secant theta times tangent theta there. Okay, secant times tangent. So the tangent Q is become tangent square times secant square. Right? Tangent times secant. Now we have the tangent square. Well, we have secant, this is secant, right? So that's your U. Actually, I need to change the colors to make things easy to read. So I'm writing here. You see the tangent square, we use identities here. Okay, the tangent square because I want so what do I want? I want a secant tangent, right? So that is the du. The secant is the u. So the tangent square need to be written in terms of secant or u. So notice that tangent is the same, tangent square is the same as secant square minus 1. Again, those are the identity you should memorize by now. And then from here, you do the substitution, right? So that is u. Secant is u. Secant, that is u. So this becomes an integral of u squared minus 1 times u squared. Right, so now we're new variables. And that's okay. Well, actually, it's better when it comes to new variable because we have a different integral, but there's no more trick. I can multiply it out and integrate from here. So we see that is distributed in, you have u to the 4th there minus u squared du. Now, if you look at this problem again, we start with x, we change the variable to theta so we can get rid of the radical. We run into the trig integral and we use a u sub to turn it into a normal integral without trig. Now you see we can integrate from here. So when you integrate, that becomes u to the 4th. I don't want to change the color now, so it's just u to the 5th over 5 minus u to the 3rd over 3. Okay, plus constant. See, integrate. I can integrate now. Now, once I finish integrating, I need to substitute back. So what is u? U, don't forget, is secant, right? This is secant. So if you replace the u with secant, then you rewrite that as 1/5 secant to the 5th theta minus 1/3 secant q theta plus c, right? Now, now we're back to the u. Okay. So now you see we're back to the theta, that's variable, u equals secant. So we got this, and then we need to express that in terms of our original variable x. So to do that, we need the right triangles. Again, you see the x here equal tangent, but don't forget that tangent is opposite over hypotenuse, sorry, opposite over adjacent. So you can think of the x as x over 1. So again, the tangent function is opposite over adjacent. I'm going to use this information again to draw the right triangle here, where my angle theta is here. It's right triangle. The opposite side is x. The adjacent side is 1, opposite over adjacent. So when you solve the hypotenuse, that would be 1 squared plus x squared equal hypotenuse squared, or square root of 1 plus x squared, or x squared plus 1. You see again, that is this square root in the beginning. Now from here, I can write then what is secant theta equal. The secant is the reciprocal of cosine. What is cosine again? Cosine is adjacent over hypotenuse. Adjacent over hypotenuse. But secant the opposites, or the opposite, the reciprocal. So that would be the hypotenuse, x squared plus 1 over adjacent side. Okay, so that's over adjacent side. So secant is just square root of x squared plus 1. So from here, I can substitute back. Here, so secant of theta is, right? So when you see the secant theta, that will be secant theta c, so it's square root, so 1/5 here, and you see that one, it's secant theta is square root of x squared plus 1 to the 5th minus 1/3 square root of x squared plus 1 to the 5th plus constant. Now we finally find the antiderivative of this functions. But do not forget that we are not done. We are not done because we are dealing with the definite integral. So that is this original integral we're looking at it from 0 to 1 x cubed plus square root of, time x times square root of x squared plus 1 dx there, right? So that's that. And then since we have the antiderivative, this step is actually pretty straightforward. You got the 1/5. Let's turn it into a 5/2, make things look a bit easier. So that's x squared plus 1 raised to the 5/2 power, right? That is negative 1/3 times x squared plus 1 to the 5/2 power. And then we're going to evaluate this, that's 5/2, from 0 to 1. All right. So you have the antiderivative here, right? Plug 1 in and 0 in. So plug 1 in, you got a fifth, and then that's 2 to the 5 half. And then that's also 2 to the 5 half. And then when you plug 0 in, so that's 1 to the 5 half is 1. So it's going to be 1/5. Plug in again, it's going to have 1/2. And then just simplify, you can just leave it as an exact form. That is the number 4.